Hey everybody, we today are going to be taking notes on section 3.2. We're talking about logarithmic functions and their graphs. Before we were talking about exponential functions and their graphs, so we're going to see how they go together and what they do for each other. So first things first is we're going to talk about some important vocab. A common logarithmic function is the logarithmic function with a base of 10. And so that word common, basically you can interpret as 10, okay? And then the natural logarithmic function is the logarithmic, I can't write, logarithmic function with a base e. And it's also given by f of x equals ln of x. As long as x is greater than 0. And the logarithmic function looks like this. F of x equals log base x, meaning log, when there's nothing there for the base, it's this assumed base 10. Okay, that's your common log, but if you don't see a base, it's assumed that it's a common log. Okay, and the logarithmic function with a base a is the inverse function of the exponential function. So we know the logarithmic function is the inverse of the exponential function, which we were just studying. And the logarithmic function with base a is defined as f of x equals the log of base a of x for x is greater than 0, aka positive, and a is greater than 0, another positive, and a cannot equal 1, and if and only if x is equal to a to the y, which is its exponential function. The notation log base a of x is read as log base a of x. So I just read that twice. And the equation x equals a to the y in exponential form is equivalent to the equation y equals log base a of x. Okay, really quick, I just want to show you something about that. If we're going from exponential form to logarithmic form, this is going to be something that you do a lot of. That if you have something in exponential form like a to the y equals x, we're going to use an acronym. We use left, right, middle. And this will work for both, going from exponential to logarithmic and then from logarithmic back to exponential, where we know if we want it in logarithmic form, we put a log, but then we go left to the right equals the middle. So we go log base a, which is the left, this is still the base, right is our x, and the middle is right here. So these are synonymous, they do the same thing, and if I were to go from log back to exponential form, I would still use left to the right equals the middle. Okay, so just to put that into perspective for you. And then if we were talking about that, actually we just did that. And then when evaluating logarithms, remember that a logarithm is basically an exponent. And that means that log base a of x is the exponent to which a must be raised to obtain the value of x. So for example, use the definition of a logarithmic function to evaluate log base 5 of 125. Basically, we're saying, okay, that means this, that 5 to some exponent equals 125. Well, I know 5 squared is 25, so 5 to the third is going to give me 125. So therefore we say x equals 3. Another way you could have done that is by using the left, right, middle. So if we know log base 5 of 125 equals, we'll just say x, we don't know, then we can solve x by putting this back into exponential form where we go left, right, middle. So we'd say left to the right equals the middle. And again, we would know x equals 3. So either one you like, you can do. And then this one's pretty simple. We're going to use our calculator and evaluate log base 10 of 300. So just keep in mind, log base 10 is your common log, and it's already in your calculator. The base that's assumed in your calculator is a log. It's no other base. So if you look at your graphing calculator, which I'm going to pull mine up, which is pretty far away, but that's okay, I'll find it. It's from September 8th. Past it. There we go, there it is. So if I'm looking, oh, look at that. I already had it there. I already did the work, but I didn't even know it. Okay, so here is my calculator. And in order to do log, I'm literally just going to hit this key right here, which is next to the 7. So when you hit that key, it looks like this. It goes log, and it does not give you a base, and then it gives you a parentheses. And then you're going to put 300 in there. Because the assumed base, it's invisible, but it's assumed to be a 10. So when we plug that into our calculator, we get 2.477121255. And that's all you got to do. All right, next one, we're going to go ahead and complete the following properties. But before we do that, we're going to write our properties of logs right here in a little chart. The first property is that the log base A of 1 equals 0. And this is because if we write this in exponential form, a to the 0 is 1. Anything to the 0 is 1. Our second property is log base A of A equals 1. And this is also, if we put that in power function, it's because A to the 1 equals A. And then log base A of A to the x equals x, as does A to the log base A of x. And that's because they're inverses of each other. So log base A of A to the x is, they're inverses of each other, they cancel out. Same as A to the log base A of x, they also cancel out. And then we also know if log base A of x equals log base A of y, then x equals y. Okay, so there's our properties of logs that you want to have written down right here. So let's go ahead and fill it in this chart right here. So we know if log base A of 1, that's this property right here, it's 0. Log base A, so some base, anytime you take the log of any base of 1, we know it's 0. Our next one, we know log base A of the matching value will cancel, and we get a 1 because A to the 1 is A. And then log base A of A, which cancel each other out, leaves me x. And A to the log base A also cancels each other and leaves me the value of x. And then lastly, if log A matches on both sides, then we know log base A of this value of x equals log base A of this value of y, then we know x equals y. Now we're going to solve the equation log base 7 of x equals 1. So let's use the left, right, middle to solve this. We'll put this in exponential form so we know taking the log off because we're putting it in exponential form. So we go 7 to the 1 equals x. Well, I know what 7 to the 1 is. It's just 7. And there's our answer. All right, part 2. If we're looking for the graph, as long as a is greater than 1, if f of x is the log base a of x, this is what it looks like. It's going to look something like this, where it has this, just like before, an exponential function had an intercept of y equals 1. This is at x equals 1, that this has an intercept. Before, the exponential function had an asymptote of the x-axis, but this asymptote is the y-axis. Okay, so that's our function for log. So over its domain, we see from left to right, it is increasing. And the domain, we can't go into the negative values of x, but we can start at 0, not including 0 because that's an asymptote, and then we go to infinity, and that the range is from negative infinity to infinity because it can go as high as we need it to. Also, the graph has the y-axis as a vertical asymptote, and the graph of f of x equals the log base a of x is the reflection of the exponential function. And remember, inverses by definition have a reflection in the line where x equals y. Okay, just really quick, I want you to have this. In order to change the value of the base, we call this change of base, in your calculator, because your log key in your calculator is already set as a log base 10, this is how you're going to change your base. So if you want your base to be some value b of some other number x, we'll say the common log of x divided by the common log of b. So just keep that in mind. You might need to use that in your calculator to find a value or to graph this. So if you want some other value of the base other than 10, this is how you do it. Okay, let's keep going. And here is our natural logs. And so we haven't done our properties yet. So we're going to put our properties right here. Here's our properties of a natural log. So remember, natural log is just ln is the same as the log base e. They're the same thing. Okay, so just keep that in mind. Don't get intimidated. It's still the same thing. All right, so log are the properties of ln. So they're similar to our other logarithmic properties. The ln of 1 is 0, and that's because e, which is, remember, ln is log base e to the 0 is 1. And then we know ln of e equals 1, and that's because e to the 1 equals e. So log base e of e just cancels and becomes a 1. We also know the natural log of e to the x are inverses of each other, so that leaves me an x, as well as e to the ln of x are also inverses of each other, will leave me x as well. And then lastly, if the natural log of x equals the natural log of y, then we know y equals x, or x equals y. Okay, make sure you get those down in a little chart. Oops. Okay, so there's my little property chart for logarithmic values of natural logs, not unlike regular logs. So the ln of 1, keep in mind, that's like saying log base e of 1. Remember, any base of 1 is 0. Ln of e, they cancel each other out, and we remember if I have log base e of e, we know e to the 1 is e, so that's just a 1. Ln of e to the x, ln of e will cancel each other out, so that just becomes x, and e to the ln of x is also x. If ln of x equals the ln of y, those values of x and y must be the same. All right, so here we go. Example number 5, use a calculator. So literally, you're just using your calculator. So if I bring down that calculator, come on, wake up. Let's bring this down. Bring it with me. Okay. So if I want to use this to evaluate my natural log of 10, here's what you're going to do. You literally use your ln key, which is right next to the 4 on the left side, and you literally type in ln, which you're going to get on your calculator will look like this, ln parentheses, and then you just plug in the value of 10. And then if you do that, you're going to get some big long value, and we get 2.302585 forever. So here we go. Plug that into the calculator. Hopefully you got that in yours. And then remember, when we were talking about the domain of the natural log, I want to show you really quick. The domain of the natural log, remember, was from 0, starting at 0 to infinity. So it can't be negative, okay? So from 0 to infinity means it cannot be negative. So the domain of this natural log means whatever's inside this parentheses can also not be less than 0. So we know x plus 3 must be greater than 0 for the domain to work. So let's figure out what that value is. Well, if I subtract over the 3, we get x is greater than negative 3. So we know our domain, if we were to put that on our x-axis, is negative 3. There's an open hole here, and it can be anything to the right of that. So in interval notation, we say starting at negative 3, not including negative 3, all the way to infinity. And that's our domain. And actually, that's it for today. We'll do the applications in class. See ya.